How are you doing today?
Doing pretty good. Doing pretty good. My can opener broke. Can opener broke. And I went to Percolate and I got a Thai iced tea with boba. Woo, so good.
Let's go back. Can go back, please?
What did you do today? Did you do anything
I
fun?
went out. I went out to learn how to drive. to know
No
how
way. Wow, that's
I know
cool.
how to
That's
drive.
cool. Wow.
I was so scared.
Oh my goodness.
Yeah, I was scared. Chapter 10, I didn't really understand chapter 10. There was a lot of information.
Okay. 10.2. I don't know. I'm gonna pick a random question like 10. All right. All right. Go for it.
In the previous year, 55% of females aged 15 and older live alone. Sociology tests whether this percentage is different today by conducting a random sample of 400 female aged 15 and older and find that 225 are living alone. Is there sufficient evidence at the alpha equals 0.01 level of significance to conclude the proportion has changed?
All right. All right. So what's going on? We got girls living alone. They're living alone. So 55% of females lived alone. Is there evidence at the 1% level of significance to conclude that the proportion has changed? Well, what was it? It was 55%. So
Yeah.
we're gonna assume that it's still 50%, 55%.
Okay.
That would be like called the null hypothesis, is that it's still 55%. In fact, the null hypothesis is going to be that p equals 0.55. It's still 55, and the alternative hypothesis is going to be that it's different. So that will be our null and alternative hypothesis. And I also want to say where p is the portion of girls living alone today. It's like there's two time periods. There is the past, which was, I don't know, previous year. It says in the previous year. It was 55% in a previous year. And then now there's right now. We want to know if right now the proportion has changed. So that's why I use not equal to, because that's what it means to have changed. Now this question wants us to test the conditions or check the conditions for being able to use a normal distribution to assume that the proportion is normal, the sampling distribution is normal. So these are conditions. What we're doing here is checking the conditions, all right? So to check the conditions, we want this to be greater than or equal to 10, whatever this is. Now, what is this? That's n. Let's get all of our things. N equals to what? What do you think n is? The sample size.
400.
Yeah, 400. Good. And then now we need p sub 0, and that's going to be 0.55. P sub 0 will be the percentage, the old one, call it the hypothesized proportion, the one that we kind of is assumed to be true. And that's pretty much it. So now we can plug in n times p times 1 minus p has to be greater than or equal to 10. So I'm going to find it. Watch. N times p times 1 minus p. So n was what again? 400, I think?
Yeah, 400.
And then p was 0.55. And then 1 minus 0.55. We check it. We get 99. Okay, good. Got 99. I got 99 problems, but math ain't one. Have you ever heard of that song called 99 Problems?
No.
It's probably an old song, too old for you.
How long?
You too young.
Oh.
I think it was like, who did that song? I got 99 problems. I don't know. It's like an old rap song. Forget who
The
did
90s?
it though. Probably the 90s or something.
Oh, I wasn't born.
All right, so let's see. All right. So we're checking the conditions. The sample size has to be, the requirements for testing the hypothesis are satisfied. Yeah, less than, see? And then this, what do we get? 99?
Yeah, 99.
And greater than or equal to? Because that is greater than. It has to be greater than, apparently. That's the only, that will go as greater than. So that's, let's see, can be reasonably assumed to be random. Okay, so that's how you check the conditions. Just say check answer. Hold on. Did we get n right?
Yeah, 0.9. Wow, 99.
What? Let's see. We got n times p times 1 minus p. 99, hold on, let's see. N is
99 or is 0.9? 400.
400 and 0.55. That should be right then. Is there other options here that I can't see because I'm on an iPad? Huh. The sample size is, let's see, less than 5% of the population size, and the, hold on, sample can be reasonably assumed to be random. Hold on. Is given to be random, not assumed to be random. They must say it's random, right? Yeah, they took a random sample. We're not going to assume it's random. It has to be random. That's a condition. So there we go. So we can't assume it to be random. It has to be random.
Because it's a random sample?
Yeah, it has to be a random sample. That's a condition. There's 3 conditions. The conditions are those. There's 3 conditions. So you could say that the conditions are 1, simple random sample. 2, 20 times n has to be less than or equal to capital N, or if you want to write it as n is less than or equal to 0.05 times capital N, that's for independence. And then the third one is that n times p0 times 1 minus p0 has to be what? Greater than 10? Greater than 10. So those are the conditions, okay? Now, okay, we can move on.
Yes.
So we can go, now, identify the null and alternative hypotheses for the test. So the null is going to be equal to the p. Do you see how it's giving me 3 options for the mean, the standard deviation, the mean and the proportion, and then alpha? That's weird that it gives alpha because that's the significance level.
So H1 always going to be like P, the proportion. H-O. That O, right? How you say H-O?
Yeah. Or H sub 0. H sub 0 because it's a subscript.
H sub 0.
Yeah, H sub 0.
0. Okay.
And the null hypothesis is always equal to.
Okay, always
equal to. And it should be equal to 0.55 because that's what we are assuming that today the proportion of girls that live alone is still 0.55. The alternative hypothesis is, like I said, same thing, P, but this time not equal to because it's two-tailed test. So there you go. That's our null and alternative. Got it?
Okay.
But the way that I want you to do it, I want you to define the parameter. So make sure you define the parameter. That's what you do right here.
So how you define the parameter? That's what we just did?
Yeah, you have to say what P is. See? P is what? It's the proportion of girls living alone today. I left out a little bit of details because it's actually 15 and older. But whatever. I'm just kind of like doing it a little quicker.
So that will be extra credit if I define it, just going to be regular credit proportion.
Yeah, you'll get credit if you do it like this. But on the test, you should be more particular. And you should, yeah, but if you want full credit, when you're doing your null and alternative hypothesis, you need to give both of these. This is the null and alternative hypothesis, and this is defining the parameter. So you got to do both of those. Even though on the homework, they only do one on the homework, because they only say what? What do they say? They only do that. Okay.
They only ask you that one, yeah.
Yeah. Now the test statistic. Find the test statistic for this hypothesis test. Okay. D naught. What's the test statistic? All right. Let's see. Let's find the test statistic. For the test statistic, it's gonna be done in the following way. Now look. So what we're gonna do is we're gonna draw a picture like this. In the middle, I'm gonna put 0.55. That's P. That's from the null hypothesis. Now it's a two-tailed test, so I'm gonna shade both sides. But what I'm gonna put right here, from the data, we're gonna say that P hat is X over N. Now let's go back up to the data and find it. We got n is 400, but we also have x is 225. It's a thing that we haven't really talked about, but that's x. X equals 225. That's from our sample of 400 girls. That's how many girls live alone, right?
Yeah.
That are 15 years and older. So let's see. So if I go down here, I'm gonna say that this equals to, what was it? 225 over 400, right?
225. Yeah.
Okay, so what is this equal to? This is about what? 225 divided by 400 is what? It's about 0.5625. Let's see, 0.5625. So that's on which side? That's on the right. So so I'm gonna say 0.5625. I'm gonna put it right there. Now, on the test, I want you to just say that this is the test statistic. But that's actually p hat. So when you guys find the p-value, I just want you to find it like this. So I want you to say the p-value equals to 2 times norm CDF, and then I'm gonna say 0.5625, comma 9999, comma the mean, which was 0.55, and then the standard error, which I'll have to show you how to get it, 0.55, 1 minus 0.55, divided by n, which is, I know it's a lot of craziness, right? Divided by 400 is, right, I know. That's the standard error, this thing, it's standard error, sigma sub p hat. Now, that's how I want you to find the p-value. So I just want you to go like, approximately what? 2 times second distribution, norm CDF, 0.5625, comma 99999, comma 0.55, comma, now here we go, square root 0.55, 1 minus 0.55, divided by 400, and that's it. Press enter, you get your p-value. What?
I say you fast. I just do what you gotta boom, 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 boom.
I know, it was too fast, right?
Yeah.
So look, I'll show you what I did. I just basically plugged the numbers in, you know, like that's all I did is I just plugged the numbers in to norm CDS.
Okay.
I plugged them in as written here. 0.5625 first, then 9999, then 0.55, then that whole radical. The last thing I plugged in was that whole radical, which is called the standard error. Notice, wait, did we double it? Make sure we multiplied it by 2. Yes, notice that I multiplied it by 2 because it's a two-tailed test. So that's my p-value. Now, the way that the book wants you to find the p-value, and now I got to talk about a difference that what the book does with the test statistics. So give me a second. Notice that in the homework, it's asking for something else. It's asking for Z. The test statistic, it wants you to standardize the test statistic. So to convert it to a Z-score, it wants you to convert it to a Z-score. Now the way we convert
0.153 Z-score.
Yeah, it wants you to yeah, exactly. It wants you to convert this score to a Z-score. It wants you to convert that p hat to a Z score. So what we're gonna do is we're gonna convert for the homework's sake, convert p hat to Z sub 0. So the way we do that, remember, the old Z-score formula was always x minus mu divided by sigma. It was always x minus mu divided by sigma. In this case, sorry, I put Z and I said X and I put Z. What's wrong with me? So it's always, that's like the basic Z-score formula. Now we're gonna change it to p hat minus p divided by sigma sub p hat. Because that's what we're dealing with now, right? Because now our X value is p hat, our mean is now p, and our standard deviation is now a standard error. So yeah, we'll have to do it like that. That's all they want. They call it Z sub 0. That's their test statistic. In the homework, they ask for that. So we could find that easily. It's 0. What was it again? What was p hat? 5625 right here. So 0.5625 minus 0.55 divided by whatever was under the radical, which we probably should have found that because it's hard to find. So hold up, let me get this real quick. Square root 0.55 1 minus 0.55 divided by 400, right? Okay, so we got that guy. Make sure you don't round that so much. 0, 2, 4, 9. Like leave 4 digits of precision here.
Okay.
But anyways, that's the standard error, so I can divide by that. So 0.0249, right? There you go. So that's your z-score as what the homework would ask for, which would be, now I gotta plug that in. See all the work that you're putting me through? No, I'm just kidding.
I'm sorry.
Don't worry, you're gonna have to do this stuff too on a test. That's
Yeah,
where
no, right?
Yeah. So let's see. What do we get? We get 0.5020. Well, that's your test statistic that the book wants. 0.5, or that the homework asks for. 0.502. Let's plug it in. Let's test it. 0.502. What is it? Round to 2 decimal places. 0.50.
Okay.
Yay! We got it right. We got the test statistic right.
That's a lot of work to get one.
Isn't it a lot of work? It's a lot of work,
yeah,
right?
It is a lot of work. There's a lot of steps.
Press OK. Now, find the p-value. Round to 3 decimal places as needed. Okay?
You already find the p-value, right?
Correct. Look, let's go back to the thing. Now, we found the p-value, right? Now, I found it here. Notice that I just used p hat as my test statistic. And I used the mean of 0.55 now, and I got 0.6, and I got 0.6153, right? I could have, alternatively, you don't have to do this, but if you do it this way, where you get this test statistic, you could actually say that the p-value equals to 2 times norm. Now you don't have to do, because I like doing it the other way, but I don't want you to find this way, but you could, if you can say 0.5020, comma 9999. That's it. And the default value of the mean.
That'll give you the same answer?
Yeah, watch. Let's check it. By the default value of the mean and standard deviation in this case is 0 and 1. Q equals 0, sigma equals 1 because it's a z-score. So watch. I bet you we get the same answer. Well, first of all, what was the answer? Where was the p-value? Did we get it? It's right there, 0.61. Let me grab that again. Let me bring it closer. Boom, 0.61. Now watch this. If I do this and I change, well, I got a lot to delete, don't I? Never mind. I changed my mind on that. I'm going to go like this. Second distribution, norm CDF.
You can get it 2 times now. 2 times.
Norm CDF. Oh, you're right. You're right. Second left. So second insert 2 times second right. See how I can do that? Second left, it brings it to the front. Second right, it brings it to the right. All right, now watch this. 0.502, comma, bang. Wow. Hold up. Why is it off so much? Why is it off so much? That's crazy. That's crazy to me that it's off so much.
Maybe because you skip 0. I'm like, okay. 0.5.
Yeah, let me try it with the extra 0. Maybe you're right. Second insert 0, comma. Oops, get rid of that comma. Let me try that. Oh wow, hold on.
That was because of a 0. It makes difference. It's the same.
No, it's not. Why is it off so much? Oh well. Oh, I know why it's off so much, because when we found the z-score, we rounded this. Remember? How we rounded the standard error. So this is an approximation. So our answer, now watch, if I do it like this, check this out. Check this, oh wait, man, oh, do I really want to do this? Watch this. This is gonna be crazy, but watch. This is gonna be insane. Check this out. 0.5625 minus 0.55 divided by square root 0.55. Hold on. Let me try this. I'm trying to do something crazy here. Don't try this at home, ladies. Don't try this at home. Don't try this at home, people.
That's a lot.
Calculator error. Okay. What? Why? Stop.
You put too many numbers.
Comma. No. Ready? Ta-da!
Is it the same answer?
Ta-da! 0.6153. Watch. If I go back up to that old one, 0.6153. 6153.02557.
Yeah,
exactly the same. See how that's the rounding. So the p-value is 0.6153. Now this, since you're doing what the book wants you to do, if you round, well, I guess the issue is in rounding this thing. When you find the standard error, if you round that, then you're off a little bit, but not by too much. So you see how I told you to leave 4 digits here? I meant it. Because the less digits you leave here, the more of an error you'll have in your final answer. Yeah. For your standard error, you need to, like, if you're gonna round it, make sure you leave 4 digits. But anyways, the p-value is 0.6153. Let's see. Don't give me a wrong. Don't give me a different number. Yeah, 0.6153. Watch. 0.615. Try that.
Oh. So that means if you find a p-value, then you find out the test that you can use the p-value later. So you're gonna ask all of these questions, the p-value and the v.
Oh yeah, I want you guys to have the most amount of fun. I'm not gonna withhold anything from you guys. I'm gonna ask you all the questions.
Okay.
Yeah.
So Paul, like when I was doing chapter 9 today, I was using the calculator to find the lower bounds and the upper bounds. So on the test, you wanted to show by the steps, right?
Yeah. Okay. I want you to show more work. Show the steps. Show all your work.
So how are you gonna show it on Canvas though?
Good question. That's a really good question.
Since you say you don't want us to email you or crash paper.
I don't know. I'll let you guys know about it. Either well, if it's on the computer, you're gonna have to type in the things that you do on the calculator. So for instance, you know how I did this. Like this is your work, you know.
You're using a pen. You don't have pen to use.
What?
You're using a pen, so you don't have pen to use with our homework. Oh, it's different.
I know. Well, you have that equation editor, right? Oh, there we go. So like when you're doing the test, you'll have to do something like this. You'll have to say
something on the last test, right?
Yeah, same thing as the last test. You do stuff like this. You'll say p-val equals, and you'll do 2. You'll just type it 2 times norm CDF, and you'll do like, okay, what was it? 5625 or something, comma. This is how you show your work, and then like 0.55, and then comma, and then here you can do stuff like this. I'm doing this on my iPad. This is crazy. Oops. This is how you show your work. Something like that. You know, watch. I do insert, and look, it inserts it. So stuff like that, you know. Anyways, so what's up? Let's see. What else do we got to do here? Okay, now, once you find the p-value, you need to make the conclusion. There's 3 steps. Step 1, write the null and alternative and define the parameter. Step 2, find the p-value. Step 3, state the conclusion. All right, so let's see. What are we doing here? Let's do like a little overview. Let's do an overview real quick. You got to go back. You got to go back and think, what am I doing here? What you're doing here is trying to test the hypothesis of whether or not the percentage of girls that live alone today is the same as a previous year. In a previous year, it was 55%. We want to know if it's still the same today. That's what we're trying to show. Our data failed, basically. It's not. It is still the same today. Our results were not significant to show that there's a difference, that things have changed, because the p-value is too high. The p-value needs to be less than the significance level, which is 0.01. So watch, I'm going to write something down for you for the conclusion. This is how I want you to write the conclusion. I want you to say this. Here's your conclusion. Hey, where are you from, by the way?
I'm from West Africa.
Yeah, what country?
Benin. No. Benin is like a little country next to Nigeria.
How do you
Benin,
spell it?
Nigeria.
How do you spell it? How do you spell it? E?
Benin. B.
Oh, B.
B. Yeah.
Oh, Benin?
Yeah. Benin.
B-E-N. I'm going to say that I tutored somebody from Benin, West Africa. Is that cool?
Yeah. Yeah.
Because that's where you're from, right? Benin, West Africa. Woo, yes. Benin, West Africa. All right. This is how I want you to do the conclusion. I want you to do a technical and then a non-technical conclusion.
Okay.
Technical and non-technical. So here you go. The first one, you're going to say we failed to reject H naught since p-value greater than 0.01, the significance level. That's alpha.
Okay.
That's your first technical conclusion. We failed to reject the null hypothesis. We failed to reject that the percentage of girls that live alone today is 55%. It's still 55%. We failed to reject that. Still 55%. So now the non-technical is there's insufficient evidence to conclude that the percentage of girls, if you want, you can include this aged 15 years and older. There's insufficient evidence to conclude that the percentage of girls aged 15 years and older that live alone today has changed. But I also wanted to mention that the technical is about the null hypothesis and the non-technical is about the alternative hypothesis. That's how I like to do it. I think it should be done like that. Just keep it consistent, always do it like that. So anyways, we have completed a whole hypothesis test. How do you feel?
More
A lot.
comfortable.
Good. Let's try number 10 on 10.3.
Okay.
So yeah, we're doing now 10.3.
Okay.
All right, yo. Here we go. Inference about the mean. All right, let's see. Can you read it for us?
Okay. A math teacher claimed that she has developed a view course that increased the score of students on the math portion of a college entrance exam. Based on the data from administrator of the exam, scores are normally distributed with a mean equal 517. The teacher obtained a random sample of 1,800 students, put them through the review class, and find that the mean math score of the 1,000 students is 523 with a standard deviation of 119. Complete part 8 to 5D below.
Thank you. All right, so look, it looks like there's something going on with like math scores.
Mm-hmm.
What's going on? There's a teacher, so there's a math teacher, right?
Mm-hmm.
They developed a review course that is supposed to increase the scores. Important word, increase. I think that's important. So this is a review course that's supposed to help students to do better, right?
Mm-hmm.
Increasing their scores.
Mm-hmm.
On the math portion of a college entrance exam. So based on the data from the administrator of the exam, scores are normally distributed. Got it. Scores are normally distributed. So if I could say something like X is approximately more normally distributed with mean 517 and standard deviation. Is there a standard deviation?
Mm-hmm.
We just know the mean actually. We don't know the standard deviation. But the scores are normally distributed with mean and some let's say
19.
Sigma, we don't know.
They give us standard deviation, right?
But they do give us standard deviation. But what is that from? That's the question. But what is that from? We need to be very careful.
The 8,000 students.
It's from the sample. So that's actually, let's be careful a little bit here. Let's not call that sigma. Okay. We don't know sigma. So I just want to make a point that we don't know sigma. We don't know sigma, which is the population standard deviation. But we do know the mean.
Yeah.
We do know the mean. It's 517. All right. The teacher obtains a random sample. Okay, good. We got the randomness. That was important. Of 1,800 students. Okay, so what's that? That's n equals to 1,800. So we know the sample size. He's taking a sample of 1,800 students to see if the mean is still 517. Now, he's trying to see if we think that the mean is going to be higher now, though. We think it's going to be higher. In fact, it is higher. It's 523. But one thing to notice about this 523 is that is actually X bar, the sample of the 1,800 students. The world wants to see you. You can't leave. No, I'm kidding.
Nobody wants to see me.
The whole world wants to see you.
Nobody knows me.
Everybody who watches this video, they want to see you, not me. You think they want to see me?
No.
All right, so let's see. So we don't know sigma, right? But the thing is, this 119, that's S. That's S. So we have X bar and S are sample statistics. We need to be very careful on what everything is in the problem.
Okay, yeah.
Yeah. I'm going to send you this video too. Don't worry about it. Like, you could always rewatch this or whatever.
Okay.
So we want to see what's up. What's the question? So what are we trying to do? Well, we're trying to see if something is increased. We want to see if the review class worked. Did it work? Did it increase the scores? That's what we're trying to figure out in part A. So part A, the null hypothesis is what? The null hypothesis is going to be that mu. We're dealing with mu, the mean now. It's going to be that the mean is still 517, or the alternative hypothesis is that the mean is greater than 517, because that's what we're trying to figure out. Does it increase the scores? So I want to define the parameter. I want to say where mu is the what? We'll say it's the mean score of students that take the review course. That's what mu is. It's the mean score of students that take the review course. It's a new course. So this is for like right now, for the new people today, take the review course. So that's how you state the null and alternative hypothesis, and you define the parameter. So this is half of it, and this is the other half. You have to define what is your parameter. It's either mu or p, that's it. Mu or p. 10.3, it's mu. 10.2, it's p. The population proportion or the mean, the population mean. That's how you do that one. You start off like that. That's step one, to state the null and alternative. How does it, so what do you think? Seem okay so far?
Yeah.
Okay,
it's
good.
Almost same as chapter 2.1. I mean 10.2 that we just did.
Exactly. It's very similar to 10.2, right?
Yeah.
Okay, good. Let's see. Let's go back to the homework and see what's going on. State. Okay, so it's going to be either B or D, because those ones say equal, right? It's either B or D. So which one is it?
I think B.
Yep, B. Good. Because it said increases, right?
Yeah.
All right, look. Find the test statistic. Okay. All right, B. Oh yeah, you're getting ahead because I haven't taught this yet. So you're actually getting ahead right now, which is good.
Yay.
Yeah, you're getting ahead. Okay, look. So I'm gonna say this T sub 0 equals, what did it want? 3 decimal places? I think three decimal places. So I'm gonna show you how to find the test statistic. Can you read this for the world? For the entire world?
Okay. Test the how you say?
Hypothesis.
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 Okay. Hypothesis, right?
Yeah.
Okay. Hypothesis at the
alpha, at the alpha.
Alpha equals 0.10 level of significance is a mean math score of 523, statistically significantly higher than 517. Conduct a hypothesis test using a p-value approach.
Yay!
That's so bad.
No, great, good job, man. Great job. You're awesome. So test the hypothesis test. Test the hypothesis at the 0.10 level of significance. This is very rich, this sentence. There's a lot of like things here. Is the mean math score of 523 statistically significant? Very good term. Statistically significant is important terminology. Is the mean of the 523 statistically significantly higher than 517? Remember, that was from the null hypothesis. We're seeing, is it 15 still, or is it bigger? Is it better? Conduct the hypothesis test using the p-value approach. Now, we're going to find the test statistic, and let me show you what it is. It's just a z-score. It's just x minus mu divided by sigma, like always. X minus mu over sigma, which equals to, in this case, x bar minus mu divided by, now instead of sigma, we're going to say s divided by square root of n. That's going to be our test statistic, because that's sigma, because we're actually going to call this mu sub x bar sigma sub x bar now. And this is actually the mean. So I know it's so many symbols, it's crazy. But our test statistic, now, in this section, we have to use a t-score. Remember in the last section, I told you to use p hat as the test statistic to find the p-value. We can't do that anymore because of the way that the calculator function tcdf works. Now think about it. Sometimes we use norm CDF, and then now we're going to use tcdf to find the p-value. So I'm going to get to that on part C. Let me we'll save that till part C. For now, let's slow down and let's only just think about this right here. And let's try to calculate this test statistic.
Okay.
So I'm gonna plug it in. Let's see, what do we have? Do we have x bar? We gotta go back. Yeah, we do have x bar and s. 523 and 119. So this is gonna be 523 minus 517. That was the hypothesized mean. 119, right? Divided by square root of what? What was the sample size? Sample size. What was it? 1800. You gotta find all those details and plug them into the formula correctly.
Yes, I have to find which one is what. I have to know which one is.
Right. So yeah, I don't know if you have a fraction bar like that on yours. Do you?
Fraction bar. Like that.
Can you show me your calculator? So I'm gonna do 523, and I want to see if you can do it. I want you to plug that in right now.
Okay.
I want you to plug it in using your calculator.
My name. I think I have to put in parentheses so I don't.
It's kind of challenging to plug this in if you don't have like an advanced calculator. I want to see if you can get it.
Okay, I will find the answer, but I don't know if it is.
Okay, you got an answer? All right, hold on. Let me get mine. I got 2.139. What'd you get?
No. I guess something different.
No, show me yours.
Oh, I just put like. Can you see it?
Okay, you did. You messed up because you're the difference. You didn't. The way you subtracted. You're only dividing into 517. You need to divide into the.
I should put like 522 in parentheses, right? Then divide it by this.
No, you should do like easier. Why not do this? Hold on. Can you see my screen? Hold on, I lost connection. Hold on. I have a better thing for you to do. But yeah, you got to learn your calculator, how it works. So basically, I want to show you what you can do. You can say 5 watts. Check this out. I'm going to do 523 minus 517. And then I'm just going to press enter.
Okay, so I'm doing that. Can I put in parentheses instead? Like, parentheses?
You can do that too.
That makes sense though, right?
You can do that. Whatever. I like this is a good way too. And then just say divided by, and then parentheses, 119 divided by square root 1800. So that's another way to do it, like that. And you get the same number as I had before. See? 2.1391. Okay.
Okay, see what I do now. Okay, I got the answer now.
Good. You got it, right?
Yeah.
So you got to practice that. Like how to use your calculator, right? Very important to practice. You not only have to learn statistics, you got to learn your calculator. People don't realize that. It's a huge issue. 2.139 rounded to 3 decimal places. Okay, let's see. Let's go back up to here. Test statistic 2.139. Plug it in. Boom.
Oh, It's an error. It's wrong.
I'm not sure why it says error. Oh, 2 decimal places. It wants you to round to 2, see?
Okay.
So we got to say 2.14. Yep, there we go. We said 3 and it was 2. All right, now, so how's that? That's your test statistic. So now we're gonna find the p-value.
P-value.
Yeah. Once again, how do we find the p-value? So look, here's a picture for the p-value for you to ponder. All right, look, in the middle, I'm going to put 0 now because I have a t-score. Oh, I forgot I was gonna show you why we have to use the t-score now and not x-bar. I forgot I wanted to show you that. Let me show you that real quick. For 10.3, hypothesis test about mu, we're forced to use T0 as the test statistic. Why is that? Why are we forced to use T0 as the test statistic? Since TCDF takes in lower, upper, and then degrees of freedom. That's it. That's the only way TCDF will work, because now think about norm CDF. How does norm CDF work? I'll just say period. Norm CDF works like this. Compare that with this. Norm CDF, we're able to do lower, upper, mean, and standard deviation. So notice that we're allowed to utilize any distribution with norm CDF. Whereas for TCDF, we have to use a standard normal T distribution. You're forced to use a T distribution, a standard normal one. Standard normal, you want to know what standard normal means? That means that mu is 0 and sigma is 1. That's the T score. It's a standardized score. So sorry, that's like a complication. You have to find the lower, the upper, and the degrees of freedom.
Yeah, so if you have to use the CDF, you have to have lower, upper, and the CDF.
Yeah, the degrees of freedom equals.
And degrees of freedom.
Right. Now that explains why right now when I find the p-value, it's a right-tailed test, and I have a t sub 0 equals to. Did I find it yet? 2.139. I think it wanted it to the. Now here's the tricky part. It said 2.14, but I'm gonna use 2.139 because it's more accurate. But I don't know if it'll mark me off because it wanted 2.14. Now that's the weird part. So that's confusing. But let's see what happens. So look, we're shading to the right because it's a right-tailed test. I'm gonna say p-value equals to t. Notice that I'm not multiplying times 2 this time because it's a one-tailed test. So I'm gonna plug in 2.139 comma 9999 comma degrees of freedom. I think it was 399 maybe. What was the sample size? 400 again or no? Or no, was it 1800 I thought, right?
Yeah.
1899. So for the p-value we get, lo and behold, TCDF, so second distribution, TCDF. Hopefully you have that on your calculator. 2.139 comma 9999 comma 1799.
Okay, let's see. Okay, I got an answer.
You got it?
0.01. Yeah, 0.01628.
Okay, so you got 0.01663, right?
No. Oh yeah, that's you rounded. Okay, you rounded. Okay, got it. Yeah.
Right. You got to round it correctly. So what I'm gonna do is check the answer now. Close the calculator, and then we'll go up to where 0.0163. Was that what it was?
Yeah, 0.0163.
So we'll go here. It wants 3 decimal places, so 0.016.
6. Yeah.
Fantastic. Okay, is the sample mean statistically significantly higher? Is the sample mean, that's interesting, is the sample mean statistically significantly higher? We'll say yes. Statistically significant, why is it statistically significant? That kind of relates to our conclusion. Do we have a alpha level, a significance level? It's weird that did they give one?
Yeah.
Oh, they did right there, 0.1. I want to focus on something. Conclusion.
Okay.
The conclusion is based off of the p-value. So watch. Technical, which is about the null hypothesis, and the non-technical, that's about H1. So I'm going to say this. I'm just going to say the following. I'm going to say reject H naught since p-value is less than 0.10. That was the significance level, alpha. We're rejecting the null hypothesis, and we are going to make a conclusion. We're going to say there's sufficient evidence to conclude that, I don't know, what were we talking about again? Something, that's where you have to go back to the question and figure out what were you talking about. The mean of a test scores after a review class, maybe? SAT scores, right? It's been a while. Increase of scores on the math. Okay, after a review course. Okay, got it. A review course. So let's see. There's sufficient evidence to conclude that a review course increases scores. It works. The review course works.
Okay.
The results are statistically significant, we could say. The review course works. It's effective. We say it's effective. Is the sample mean statistically significantly higher? Yes. That's pretty much it. I was trying to like check the answer, but I must have got logged out somehow. Let me see if I can refresh. Will that help? Oh look, let's try it. There we go. Okay, anything else? Do you think that a mean math score of 523 versus 517 will affect the decision of a school admissions administrator? In other words, does the increase in the score have any practical significance? Probably not. It's too close. I would say no, because the score became, it's not that much. There's not a lot of practical significance. I would say that. So there is statistically significant evidence to conclude that the review, that's very interesting. I think that's super interesting, right? Because it seems like the review course, it works in increasing the scores, but the scores only increased by 6 from 517 to 523. So that's only a 1.6% increase. So I guess there's not practical significance, but there is statistical significance. So I don't really talk a lot about that, but I think that's kind of interesting. I should probably start talking more about that because it is kind of important. I'm glad that it does it in the homework, actually. So this is saying something else. I mean, it's saying test the hypothesis at the alpha equals 0.1 level of significance with n equals 400 students. Now, these results are not, I can tell you right now, I'm predicting that they're not going to be statistically significant because the sample size is smaller, which is going to make let's see, when the sample size is bigger, we had more information. Here, the sample size is smaller, so we have less information. So that causes the test statistic to get wider. So the probability, the p-value is actually going to get bigger. It's going to get bigger. That's a little bit hard to see. The t distribution is going to get wider. So even though our results are at 523, so like basically what I'm trying to say is I can't write. I need to go back to write. But look, let's just finish reading it. There's 400 students now. Assume that the sample mean is still 523 and the sample standard deviation is still 119. Is the sample mean of 523 significantly more than 517? Do the same stuff. The n is going to change to 400. So it's going to change. The p-value will also change. They'll both change in this case. I thought that it might stay the same, but I was wrong because you're dividing by 400. So that's going to be different. But it's very interesting that because of the sample size changing, our p-value is going to be higher and it's not going to be statistically significant because the sample size got smaller. I'm predicting that the results are not going to be statistically significant, even though X bar and everything, even though X bar is the same. Watch, let me show you something amazing. I like this question so much. Where are we? Because look, I want to show you a little comparison. Check this out. In the question above, when n was 1800, the t distribution was more compact. So you had 523 was here, or was it 517? I think it was 517. 523 is like right here, right? Look at this. Look at how cool this is. The t distribution is more narrow. because n is big, as n increases, it gets more compact. Now watch this. When n is 400, the t-distribution is wider. So it's actually like that. So watch. So even though 523 is in the same spot, do you see that it is bigger? You see that like this shaded region is bigger p-value.
So how come though? This is 400, this is 1,800, it's 1,800.
This is wider because of two reasons. First of all, I talk about this in another video on my most recent video on this. Watch, let me show you something real quick. Let's see if I can pull this up. Now what? 1800, n equals 1800 versus n equals 400, right? That's what we're talking about, right? Now watch this.
Yeah.
So what's up with increasing the sample size? All right, this margin of error has two components. It has t star and it has this standard error, okay? So we're gonna focus on the standard error now. So there's gonna be two parts here. As n increases, it's gonna make this smaller, and then secondly, as n increases, something's going to happen to t star. So I wanna focus on two things right now. The critical value a little bit more and the standard error. Right now we're talking about increasing the sample size. All right, check this out. We're increasing the sample size, right? We got n equals 5, we got n equals 50.
Now remember, there was 400 and 1800, right? 400 and 1800. So 400's on the top and 1800's on the bottom, according to this graph, right? So watch.
And you got n equals 500. Check out what happens to the graph as you increase the sample size. The smaller sample size is wider, and that's because the standard error is directly related, inversely related to the sample size. Do you see this? This is the standard error, this thing right here. So let's take a look. For the smaller n value, you're dividing by a smaller number, which makes this fraction the biggest. 0.894 versus 0.283 versus 0.089. Do you see that? It's the relationship with the denominator and the fraction. As the denominator gets bigger, the whole fraction gets smaller. So as you increase the sample size, the standard error gets smaller. You see that? As you increase the sample size, the standard error gets smaller. So if the standard error gets smaller, what happens to the margin of error? Well, they're directly equal to each other. So as one gets smaller, so does the other. So that answers the question. Part one, as you increase the sample size, you can make the margin of error you can make this smaller, and your confidence interval will be more accurate. All right, so the first part about increasing the sample size is that it makes the standard error smaller. Part two, also, something very interesting happens to your distribution as n increases. So not only does the standard error get smaller, making this more compact, but so does your distribution change. So I want to consider a confidence level of 90%. So in here, this percentage is 90% on all three of these. But wait a second, why is this one smaller if the percentage is 90% on all three of these? Well, we saw one reason is because the standard error is getting smaller, but also I'm calculating inverse t for three different sample sizes here. And notice that as the sample size increases, the t star gets smaller. See that? For a sample size of 5, you have a critical value of 2.015. For 50, you have a critical value of 1.676. And for 500, you have the smallest critical value. So why is this happening? Because the t distribution is getting more narrow as n increases. This is the most narrow graph, and n is the biggest. For smaller sample sizes of n, it's really flat and wide. The t distribution is really flat. But as n increases, it gets more narrow and it approaches a normal distribution. So that is another reason why the margin of error gets smaller as the sample size increases. Now, with regards to that, I want you to keep in mind one thing. We do not know sigma, right? We are using S because we do not know sigma, the population standard deviation. So to compensate for that, we need to widen the distribution. So the t distribution is wider for smaller sample sizes. But as n gets bigger, the sample size, S approaches sigma because we have more data. Therefore, the t distribution approximates a normal distribution and it gets more narrow because we're more accurate because we have more data. All right, so let's sum it up.
Yeah. So
It's on YouTube?
yeah, that's YouTube.
Okay. Now I understand.
That is why.
Because in the N is more smaller, the graph will look better.
Yeah. So when n is bigger, this thing gets more compact, right? When n is bigger, this is more compact. So this value is further away. So the area here is smaller. When n is smaller, it gets wider. So then this thing is like closer. These are closer together, relatively closer together, relatively. So but now they want you to repeat. They want you to repeat the process with n equals 400, and I bet you money that it's not significant if you were to repeat the process of finding the test statistic and p-value. Where do we find the test statistic? I think we found it right here.
Yeah, that's it. Yeah.
So if you redo this and change n to 400, I bet you this number will get,
Small. I mean,
small.
bigger.
Let's see. Will it get smaller? It should get smaller.
Yeah, bigger. No, should be
It'll
bigger.
get smaller.
I think it'll get bigger.
No, because look, when n is smaller, this value is smaller. See, this thing is like 2.1, how many standard deviations away? 2.139. 2.139 standard errors away. It's farther away. This one's farther, right? Guess what this one is? This one, whenever we find this, it should be closer. That's the thing. It should be closer, right? Because this area is bigger. It's got to be closer. So this test statistic should be smaller because it's closer to 0. It's closer to 517. So if we were to plug it in, that number should be closer, smaller. Watch. All you got to do for me, all I got to do is go do 523 minus 517, enter, and I do divided by, what was it? 119? Divided by square root of 400?
Yeah.
This should be smaller than 2.139. See?
Yes, it gets smaller.
1.008, so that's 1.008. Oops. And now, obviously, when I find the p-value, it's going to be TCDF 1.008, comma 9999, comma degrees of freedom 399, and that's going to be a what? Will that p-value be bigger or smaller? The last p-value was 0.0163. Now, what do you think about this p-value?
I think it's gonna be smaller.
Smaller?
Probably 1.00. Yeah.
Now, think about this though. You're misunderstanding this p-value. Look, this is the p-value right here. See these p-values? Which one's bigger?
Oh, okay. It's gonna be bigger.
Yeah. So since the p-value is bigger, we have less evidence to reject the null hypothesis. So anyways, what do you get for the p-value?
0.1.
Second distribution, TCDF 1.008, comma 99999, comma 399. Did you get it?
Yeah.
0.157. It is way bigger. Way bigger.
Yeah, it is bigger than the first one. The first p-value.
Yeah, the first p-value was small. It was somewhere here.
It was 0.16.
Right?
Yeah.
That was statistically significant. Now, it's not statistically significant. That's what I predicted because the sample size got smaller, so you had less data. Your results were not as significant. So now you would say reject. Oh, sorry, you would say fail to reject. You say fail to reject H naught since p-value greater than 0.10. I think that was the significance level. And then you say there's insufficient evidence. It's a great question. Insufficient evidence to conclude that the review course increases test scores. See that? So now we say that our results are not statistically significant. Whereas before they were statistically significant because we had a bigger sample size. So now you know a lot, man. 10.1 and 10.2.
Yes, I do. Thank
I'll
you
see
very
you.
much.
We good for the day?
Yeah.
I'm gonna send this email. I'm gonna send this video. I'll put it up. You can watch this video, and I think
Yeah.
you'll help a lot of people. The whole class.
Yeah.
They'll be thankful for you doing this video with them. This video is gonna help so many people. Wow.
It's almost 9 o'clock, so yeah.
Good work, Christiane.
I like it though. I wish I could do it every weekend.
I know. We should do it every weekend.
That's helpful.
Yep. All right. Well, glad I could help you.
Yeah, you did help me. Now I have more understanding now.
Yeah. All right then. Have a good night.
Thank you very much. Good night.
All right. Bye.
Bye.